Welcome back. You know that moment when you press a button on your game controller or your keyboard and your hero character jumps or performs an attack? Well, today we are going to take a look at exactly what handles all of that behind the scenes. The input system acts as a universal translator, which allows our game code to fully understand exactly what our player is trying to do. What you are currently looking at on your screen is the standard default configuration provided directly by the Unity engine, which serves as our primary starting point for developing high-end AAA gameplay. Let's see what it is that we are facing. On the left side, we have the action maps. These represent the various contexts, though you see the player and the UI. This means we can utilize entirely different control schemes whenever we are engaged in combat or navigating through our game menu. That is absolutely brilliant, right? Moving forward, we now shift our focus toward the very center of the design. It is right here in the center that we discover the core of the action. These represent the essential verbs of our game, such as moving, jumping, attacking, and various others. This is where we determine exactly what our protagonist is capable of doing. Looking to the right of the screen, we find the Properties panel. This is where we dive into the finer details of our setup. A command is just a simple button input. For instance, pressing a button to attack or jump. Alternatively, for fluid movement, like a controller stick, we use the dedicated value section. Here, we have total control over every aspect, but many developers are happy using the standard tools Unity provides out of the box. However, we are gathered here today to transform ourselves into genuine professional developers, rather than simply remaining casual users. Relying on the default package is certainly convenient, but if you truly aspire to craft unique and original mechanics, you must understand how to construct this entire system from the ground up, piece by piece. Take a very good look at this list right here, because in just a few seconds, we are going to make it disappear. In this lesson, we are not just going to be sitting here watching. We are going to build our very own input system from the ground up. We are going to define our maps, our actions, and our keys. Only then will you have absolute control over the feel of your platformer. Are you ready to get your hands dirty and start building? All right, let's wipe the slate clean and start over.
In this lesson, we will make a huge leap in quality. Many people settle for what Unity offers by default, but we are here to build. Let me briefly show you the default input system. Let's double-click. See? Action maps, actions and properties. It looks complicated, but we will master it shortly. Let's close everything and prepare our workspace. Let's go to the project section. Organization. First of all, let's create a new folder and name it Input. Let's move the default file inside. Right-click, create arrow input actions, and rename it Controls. It appeared. Double-click, and our control panel opens. It's empty, clean, and completely ours. Let's start with the action maps. Up here, there's a plus sign. Click it and type Player. Here, we will put everything related to movement. But look, if we add another map called UI, I'm creating a different context. Why? Because when you are in a menu, you don't want the character to jump while you are clicking settings or audio and so on. Separating contexts is the foundation of professional game design. Now let's go back to Player. Here is the generated action. Let's delete everything. Right-click arrow delete. Click the plus sign to add a new action and name it move. Today we will focus on movement. Pay attention. Here in the properties, the type is set to button, but for movement, we don't need an on/off button. We need a value. Let's delete the default binding of move and add a 1D axis. One dimension. It has a negative and a positive value. It's pure mathematics applied to fun. Guys, before mapping a fundamental ritual, click on Save Asset. Never forget it or you will lose your work. Let's close it. Go to our hierarchy, select our player. Now look closely at the inspector. I'll move the mouse over and tweak the position.x value. Going negative moves it to the left. Moving positive moves it to the right. Is the value clear to you now? Let's go back to our controls. Double-click and select negative. So for the negative, we need to assign the input to a key that goes left. In the properties on the right, click on the path field and choose the keyboard. Don't search through the endless list. Click on Listen. Press the A key on your keyboard and select it. Perfect. Now, when we press the A key, it will move us left. We need to repeat the action. Repeat for the positive. Click on Path. Same exact thing. Listen and press D. Very well. Now let's do a pro trick. Since I don't like using the classic WASD keys to move when playing platformers, but prefer the arrow keys, let's do this. On our positive, which is the D key for right, press Ctrl plus C and Ctrl plus V. It has duplicated. In the new binding, change the path from a generic key to an arrow. Type arrow in the search bar. Perfect. Right arrow. And do the exact same thing for the negative, setting it to left arrow. Very well. Let's duplicate again. And in the path, this time we go to Gamepad and select left stick /X. Remember the X-axis because we are using a single dimension. There you go. A universal system created in just a few seconds. Our move is now full of bindings, but it's a bit messy. Let's use control schemes. At the top, above the action maps, click on No Control Schemes. Then Add Control Scheme. Create it. Type keyboard and save. Now click on our bindings. Look, in the properties, there's a field for the control scheme. Check them one by one, obviously only for the keyboard keys. Only the left stick is left out. Go back to the control schemes. Click on Add Control Scheme. Create Gamepad and save. Now in the properties, check the corresponding boxes for each binding. If I select the Gamepad profile, I'll only see the stick. This, guys, is professional developers organization. It's mandatory. Remember, click on Save Asset. One last touch. Let's create the jump action. Here the button type is perfectly fine. In the properties, map the key for the keyboard just like we did before. Assign space. Very well, now duplicate it. Do the same operation. And for the gamepad, we go and look for button south, which would be the A or X button on the controller. Remember to check their respective control schemes. We have built the brain of our game. In the next lesson, we will connect these impulses to our players' muscles through code. See you there.
Are we ready? I know you are. Let's select our input system asset named control. In the inspector, check the generate class box and click the apply button. Unity has just automatically created a script, and our translator converts the pressed keys into instructions that the code can understand. Let's move into our scripts folder, which is currently empty. Right-click, select Create greater than C# script, mono behavior, and rename it Get Input. This will be our data collector. It acts just like a warehouse worker. Its sole job is to take the signals from the input system and keep them ready for our player. Crucial step, select the player in the hierarchy. Click Add Component in the inspector and search for player input. Notice how Unity loads a default system here. I left it there on purpose to show you how to change it. Open the input folder and drag our control file into the action slot. See that? Now our custom action maps appear, player and UI. Make sure you select player. Let's go back to our scripts folder and double click on Get Input. Let's dive into the code. At the very top, add using Unity engine.inputSystem semicolon. To unlock the commands, let's create a private variable of type control and name it myControl. This is the space where we will store our input system reference. Next, we need a float variable. Let's write public float and name it value x, which will capture the negative or positive value from our x-axis function. Now let's type awake, leveraging Visual Studio's built-in AI intelligence. It suggests awake, which is exactly what we need. Hit the tab key and we've generated the awake function. Why is it called that? Because it literally means to wake up. It's the very first thing that triggers when the game is born, even before the player appears on screen. Inside this method, we write myControl equals new control. This is necessary to physically instantiate our command object. Now let's create a function and name it onEnable. What is its purpose? Literally, onEnable means upon activation. This function runs every time the player object is turned on in the game. Inside we write myControl.player.enable. It's like flipping the main power switch. From this moment on, the player is ready to listen to your keystrokes. Now let's delete start and update to keep things clean. Let's create a new method and write private void, naming it start move. And inside the parentheses, we type input action.callbackContext CTX. Let's use an abbreviation. What is CTX? It's short for context. Think of it as an envelope that Unity delivers to us. Inside, it contains information about which key was pressed. Inside this function, we write value x equals ctx dot read value parens semicolon. With this function, we open the envelope and read the numerical value of the movement. If we press the left arrow, it will return a numerical value of -1. If we press the right arrow, the numerical value will be 1. Now let's go back to OneNable. Notice that the IDE suggests a function, but look closely. In our controls file, the action is simply named move. Never trust automation blindly. Let's delete the X and write my control.player.move.performed plus equals start move semicolon, which references the function we just created. Let me explain how this works. The plus equals symbol tells Unity, as soon as the move action is executed, performed, also trigger my custom start move function. Got it? Let's head back to Unity, select the player from the hierarchy, and drag the getInput script onto the player. Now let's create the player move control script. And add it to our player object. Here, we will define our movement speed. The reference to our getInput script, and then our rigid body 2D component. Inside the start method, we use getComponent to gather all these references. Observe carefully. See the update method right here? We are going to use fixed update instead, because the standard update method depends entirely on your computer's frame rate. If we have a slow PC, update will run slowly, whereas fixed update maintains a hard-coded fixed interval. It runs at a constant and precise pace. Since we are managing physics via the rigid body 2D, we must be consistent to prevent the player from stuttering. Now inside fixed update, let's write rb.linearVelocity equals ... We initialize it with a new vector, passing in our movement speed, and then multiplying it by the value from getInput, which handles our positive and negative directions. Everything else here remains at default. What are we doing? We are moving the player by multiplying speed by the direction provided by getInput. Let's save everything and switch back to Unity. If we click on the player in the hierarchy, we can look over at the inspector. Let's assign a value of 1 to our speed variable, otherwise the player won't budge. Now press play. Keep a close eye on value X. Press the left and right directional arrow keys. It shifts correctly between 1 and -1, but the player just face planted. Poor guy, that had to hurt. Let's hit stop. Now look closely at the Z rotation inside the transform component. Physics forces are causing the object to rotate. To fix this, go to the rigid body 2D component, find the constraints section, and check the box for freeze rotation Z. Now the player will stay upright. But we have another issue. If I release the keys, the character keeps walking indefinitely. Let's jump back into our getInput script. We need to create a stop move function and set value x equals 0. Next, let's head to onEnable and add myControl.player.move.cancelled plus equals stop move semicolon. Notice that unlike the previous setup using performed, here we use cancelled. This means the player has released the button. And finally, let's implement onDisable to handle deactivation. Here, we use minus equals to unsubscribe from these events and disable the system entirely. Shutting down your controls properly is essential to prevent leaving useless background processes running and to save memory. By utilizing onDisable, we guarantee that we are optimizing memory allocation efficiently.
In this lesson, we'll address a fundamental aesthetic problem in animation. Look at this character on screen. We don't want our heroine moonwalking like Michael Jackson. We want her to turn naturally. Instead of a full 180-degree turn, we'll use a clever mirror trick to fix it. Let us adjust the scale value on the x-axis, changing it from 1 to -1. See that? It is fast, lightweight, and it works perfectly every single time. Now, we are going to teach the code to perform this task for us. Let's open up Visual Studio and navigate into our Player Movement Control class. To start off, we are going to need a variable to keep track of exactly where the character is looking. So let's go ahead and write private in direction. We initialize it to 1, we assign it a value. We use an integer because the direction is clear. Either it's 1, which is positive and goes to the right, or it's -1, which is negative and goes to the left. Unlike the floats used so far, we don't need decimals here. See? Now, let's go ahead and create a function. Let's write now. Go ahead and execute the private void flip function for me. We are currently writing an instruction inside of here. And let's write if gi, which stands for the getter input dot value x property for the new variable that we have just created, which is of the integer data type with a direction of -0. Let us pause here for just a second. It is a matter of pure, simple logic. If we take the key input and multiply it by our current direction and the resulting value is less than 0, it means we are pressing the key that is opposite to the direction we are currently looking. It is only in this very specific case that we actually enter the logic contained within our if statement. Now, moving inside of our if statement, let us go ahead and write transform.localScale equals, and then we will assign it a brand new vector 3, which is simply the negative value of our current transform.localScale x, while keeping the original y and z values. Let's review point 1 and then point 1 again. Tell me, what are we actually doing here? So, transform.localScale controls the size of the object. We are using a new vector 3 because the scale property requires all 3 dimensions. Notice that we only utilize the x, which is the dimension we move along, both left and right, representing the horizontal axis. Even though we only use the x, it still contains 3 dimensions. So please look at this very closely. X, atto x and then y, which stands for the vertical axis or the height, and finally z, which represents the depth. By simply placing a minus sign in front of the x value, we are telling Unity to flip the character just like a mirror, while leaving both y and z completely unchanged at a value of 1. Immediately following that, we are going to write the line direction equals -1. This specific instruction is what updates the value of our variable. If the value was previously 1, it now becomes -1, and if it was -1, it becomes 1. By doing this, the code will always be able to keep track of the very last direction that we were facing. Instead of leaving all future actions in fixed update, let's create a new function, private void move. Se zeoditarita dueke dishana. And then we go ahead and write the flip command. And inside of the fixed update, we paste the move command. Finally, within the fixed update, we only call the move function. Why exactly do we choose to do this? It is to keep our code clean, organized, and structured. Our character will perform many other actions, and we want to ensure each function has its own specific dedicated task. Now, let's save all of our work and head back over into Unity. Take a look at the local scale values shown in the inspector. As we press the keys, they change instantly. The result is perfect, and the code is written by true professionals. Lesson over for today. In the next lesson, we'll move on to animations. Let's begin. Let's select our heroines folder in the Project Assets section. Double-click to open the subfolder and go to Model. Here we have our game model. Now let's make a duplicate. Command-C and Command-V. Observe the duplicate in the Rig section of the inspector. It is set to humanoid. Imagine Unity as a translator. The model speaks a language called Bones. If it were on generic, Unity understands that there are moving parts, but it doesn't know which are the legs and which are the arms. So let's leave it set to humanoid. We are telling it, hey, look, this is a human being. Without this, your hero would remain as stiff as a broomstick. Now let's drag and drop it onto the desktop. Make sure to use the copy, not the original. Now I'll take you to a magical place, Mixamo. Why do we need it? Because creating animations by hand requires infinite patience or too many coffees in your system. Mixamo gives us the work of professionals for free. Sign up, it's free. I use my Facebook profile for the login. Look closely in the character section, we can use all these models. I'll pick one at random. Now let's select animation, and in the search bar, I'll type running and choose one of these. See, the character escapes from our framing. Let's check in place. It's vital. In a video game, it's a nightmare if the animation moves the model. We want the script to decide the distance covered, while the animation should only simulate a movement on the spot. Otherwise, it runs out of the camera view, and you'll be cursing in 14 languages. Now let's do upload character. And let's look for the model from the desktop to see the animations directly on our heroine. But I like the running effect I selected. Let's go with the download. So in the download here, there is the option to do with skin or without skin. I choose with skin because often without skin
Mixamo is not compatible and you find yourself with an arm backwards or a crooked foot. It looks like the character was hit by a train. Let's download it and drag it into our animation folder. Very important note. Select the imported object in the rig. In the inspector, set it to humanoid again and click Apply. Let's switch to animation. Check under loop time. Now let's do some cleaning. Open the object, find the animation symbol where it says Mixamo. Let's do Ctrl+C and Ctrl+V. For those who have a MacBook, you can do Command-C and Command-V. Now, if you notice, the animation is outside, so it is free. Let's delete the original file and rename our clip to running. Let's go back to Mixamo and search for the idle animation when standing still. You choose the one you like. I'll go with this one, like this. Let's go to our hierarchy. Inside the object, in the child object, which is our model, right click with the mouse and select Prefab, Unpack. This serves to unbind the model and work on it from scratch. Let's delete the old animation. Now, in the animation folder, right-click Create. Animator controller. And let's call it Player Anim. This right here is the character's brain or the steering wheel of the car. Let's select the player from the hierarchy. Go to the inspector, click the Add Component button, and type Animator. Very well. Now, from the project window, let's drag our player anim. Double-click to open it and drag our running animation inside. See that it turns orange, so it's the default. Now I'll show you how to open Windows differently at the top on Windows, same for animation, moving it near the console and project tabs. Now let's do a test by pressing play in the animation tab, but it doesn't move. It's a classic mistake that makes you throw the mouse out of the window. Obviously, the avatar is missing. The avatar is the bridge. It tells Unity to take the movement from the animation and pass it to the model's bones. Insert it in the inspector and you'll see the magic. Now she runs. Fantastic. Let's go back to the Animator and drag the idle animation. See this box. These are called states. The character cannot run and stand still at the same time, unless they are a politician. So right-click with the mouse on idle. Select the option, set as layer default state. So the first thing it will do is stand still. Otherwise it would run even while waiting for the bus. To test, switch from running to idle in the animation window and click play. It's the fastest way to verify everything without wasting time. In the next lesson, we'll start the engine with code. Observe, our player is in idle mode, but look closely. It looks pixelated, right? Let's move closer to the game view and uncheck low resolution aspect. Why? Because Unity by default halves the pixels to save resources, but we want the maximum quality. Now let's exit free aspect and set a fixed resolution of 1920x1080. There we go. Now the pixels are perfect, so we get that wow effect. Now let's go into the Animator. Here you can see the states. We are on idle by default. If I try to move the default to running and pressed play, she would run constantly. Let's bring it back to idle. Idle is in orange as the initial state. And look closely at these three nodes. Entry is the starting point. The arrow coming out of it activates the default animation as soon as the game starts, while exit is used to close an animation cycle. Then we have any state. It's extremely powerful. It allows you to jump to a specific animation, such as death or damage, starting from any other state without having to create 1,000 different arrows. Now let's move to the top left under parameters. This is where the variables for our code are. They're created from here. Before selecting float, let me show you that there are many types of variables. We will use them later because right now we need to use float. Let's go back to Unity and move the x value of the transform. See all those decimals after the comma? That's why we use float. We need them to read the character speed with millimeter precision. Now let's go to parameters. Create the float variable and call it speed. Now let's create the transition. Right-click on idle. Select Make Transition and point it towards running. Now let's select the arrow, the transition we just created in the inspector. As you can see, there are many fields. Let's zero everything out. Transition duration to 0. Uncheck has exit time. We want 0 delays. Below under conditions, let's add speed. It suggests it and gives it to us right away. Speed greater, and let's write 0.01. Why exactly 0.01? Because physics systems almost never reach a perfect zero. There is always a tiny residual movement, so by using 0.01, we create a dead zone that prevents the running animation from jittering or starting by mistake. Now let's do the opposite from running to idle, this time with the less condition. If we press play now, nothing happens. The general command is missing. What would that be? The code. Let's go into the script. Player move controller. Let's declare the component. Private animator anim. Let's initialize it with anim gelcombellanont. This tells the script where to find the animator on the player. And now let's create a new function. Private void animate. Look, Visual Studio suggested it to me. Now I will explain step by step what this code means. So let's explain the details clearly. Anim stands for our animator. setFloat stands for the type of variable we added in our animator, and then speed is the name we gave it. In short, it's the command bridge. It sends the numerical data to the speed variable we created in the animator. Then we have this name here, math. Negative numbers for left, for example, -5. And positive for right, for example, 5. Okay? So Unity does this, but our heroine's legs must run in both cases. However, the animator only understands numbers above 0, unlike Unity. In practice, it's a magic filter. If you give it a 5, it returns a 5. If you give it a -5, it erases the minus and returns 5. This way, the running animation will always work. No matter which direction you are going, it works to trick the animator. Okay, then we have this RB leger velocity x. This is the actual speed calculated by the physics engine. We don't use the text input but the body's velocity. Why? Because if the character gets pushed by an explosion or slides on a conveyor belt without pressing any keys, the animation will still trigger in a realistic way, and it's beautiful as far as physics is concerned. Then we call animate inside the update method and test. Fantastic. Check in the properties. The action type must be set to submit. It's fundamental because the jump is a single impulse, not a continuous value. Then below, in the binding, make sure you have assigned the space key for the keyboard and the south button for the gamepad. If this is not set, the code we are about to write will speak to a vacuum. Now, to avoid wasting time searching for files in folders, go to the inspector on Get Input, hover the cursor over the center of the component, and double-click Magic. Visual Studio opens up. Now let's prepare the switch that will communicate with the rest of the game. We write a boolean variable public bool jump input. This will be our switch. We need it to tell the rest of the code whether the button was pressed or not with true and false. Now we create a function. We call it jump start. And we assign it the value jump input equals true. And right below, when we release the button, we create the function jump stop and give it a false value. Now let's connect the events in onEnable. We write myControls pylon jump performed +, and we assign it the newly created function jump start. Do the same in onDisable, but with the minus sign to disconnect them. We do this because if the object were destroyed, Unity would keep trying to send the signal to a button that no longer exists, creating memory leaks, and we definitely don't want that. Now, let's save everything and move on to our player move controller script. We create the method directly creating a function that we call jump player. Inside, we write a check. If the switch is turned on, we give velocity to the ridge body. Hold on everyone. Unity shows an error on jump force. Let's go up among the variables and declare it as public float jump force. Now the error disappears. Now we call the method inside typeized. Let's go back to the method, and after the jump we write g input jump input. And we assign it the value false. This resets the input. If we don't do this, the player would keep jumping every single frame, as if they had the springs under their feet. Let's save and go to Unity. Let's turn up the jump force variable in the inspector, otherwise it won't move even with prayers. And let's test it. It works. Let's solve this with laser sensors. So now we need to tell the game who is the floor and who is the player. In the inspector, we go to Layer, click Add Layer, and create a player layer and a ground layer, because we will assign one to our character and ground will be for our floor where we touch terra firma. Let's assign them right away. Now let's go directly to project settings, select physics 2D, uncheck ground, and leave it checked only on player, while on player we uncheck everything. We do this to optimize the game, preventing the rays from colliding with the character's own body. Now let's select the object inside the player and bring it back from 90 to nil. This will be temporary. Select player and create two empty objects. Empty object, which will be children of the player. Rename it point left. Let's place it under the feet. Now copy and paste. Rename it point right and move it to the right foot. Position them properly, one on the left and one on the right. Why 2 points? It's for the Raycast. If we use a single ray at the center of the body, what would happen if your hero found himself with 1 foot off a ledge? The ray would pass through the empty space and the character would remain stuck without being able to jump. So a bug would be created even if visually he still has the other foot on the rock. By using 2 sensors, we cover the entire base of the character. If at least one of the 2 touches the ground, the jump is guaranteed, and it makes the difference between a game that feels broken and one that responds to commands like a glove. Select the object inside the player and bring everything back to rotation at 90 degrees. Let's go back into the script and write the variables we will need to make our sensors work. So we write a variable of type float, we call it ray length. This is the length of our ray. Imagine it as an invisible tape measure that starts from the feet and goes downwards. A variable of type layer mask, and we call it ground layer. This is a filter. The ray ignores everything. It only responds when you hit the layer we called ground. Then a variable of type transform. We will actually create two of them. They will manage the right foot and the left foot, the empty objects we created. So they will be our starting points. They indicate to the code the exact position, x ipsu rolli, from where to trigger the laser under the feet. Then the last one, a boolean we call it, is grounded. This is our final response. It will be true if we are touching the ground, it's false if we are in empty space, like if we are jumping or falling into a ravine. Now we write a method and call it check status. Let's analyze what we are telling Unity word for word. So ich zeigt do die left hit. We are creating a container called left hit. Okay? So this container will store all the information about what the laser hits. Then we have physics 2D Rorschach. It's the command to shoot the laser. Then point left ball position indicates the exact spot where the laser starts. The left foot and then vector 2 down indicates the direction of the laser downwards. Ray length indicates how long the laser should be. If it's too short, it will never touch the ground. And then there's the last one, ground layer. This is a filter. It tells the laser, ignore everything else. Only respond if you hit the floor. And then we repeat the same line for the right foot. Now that we have shot the lasers, we need to interpret the results. We use an if statement to decide if the player is on the ground. We write if left hit collider null, then you see these symbols. It means or if there is one foot and the other is not and it's outside the ledge, you have to say yes. So the value is either one or the other, or both is yes, otherwise no. Now let's go update the jump. We create an if inside the if and write g input jump input. And we cut the function and insert it in here. And we pass the check status function into type-for-dice. Save. Select the player, and immediately in the inspector, in the ground layer script, we set ground. Now let's drag our created objects into our player point left and point right. The jump is solid, it's ready for release. Let's go back into the script, add this function, we write on draw gizmos or debug draw array. This is used to see the rays. We use debug draw array and set the color to green if it touches and red if it's in the air. We call this function inside check status. And let's go to the inspector. We set the values for the length of our laser. Let's activate our screens because we can only see it in the scene view. So we also need the command from the game view. Let's split the screens so you can also see how it works. Let's observe carefully. We programmers don't have X-ray vision. Without this method, we are coding in the dark, hoping that the sensors work. While with debug draw array we have laser vision, and it's a fantastic thing that we can know where we touch. If it's green, it's touching. If it's red, you are airborne. If something is wrong, you see it with the naked eye. Without going crazy over 1,000 lines of code, very well. That's all for this lesson, and we'll see you in the next one with the jump animation. Let's go to Mixamo and get what we need. Jump to take off and fall for the dive. Let's download them. Make sure the check mark on in place is active. Let's bring them into the project. Select the files. Go to the Rig tab and set it to humanoid. Click the Apply button immediately. Otherwise, the Mixamo assets will remain dead pieces of code with no life. Now let's go to the Animation tab. Activate Loop Time, go into our Animator, and head to the section Parameters. Here we create the senses for our player. Create a float and call it V-speed. This tells us whether we are going up or down. And then we also declare a boolean and call it grounded. This is the switch that tells the game if our feet are on the ground or if we are airborne. Right-click with the mouse and create a state. This one is new. Blend tree, and let's name it jump. Why do we use it? Because instead of making ugly, sudden cuts, the blend tree smooths out the animations. It's a mixer that uses the body's velocity to decide how much rise or fall to show us. Total fluidity, right? Double-click and let's enter the heart of the system. Important parameter set to the new variable we just created, vSpeed, which stands for vertical speed. Let's add two motion fields. We throw the fall file on top and jump below. Now let's change the parameters. Uncheck this box, and for the fall file we set it to -1, and we set jump to 1. Look at the red bar. Now physics controls aesthetics in real time. More professional than this is impossible. Click here on base layer. Let's connect any state to our jump. In the arrow settings, zero everything out. Transition duration, everything. Why? Because we want the jump to start instantly the moment we press the jump button. Let's set the condition on the arrow. You only enter the jump when grounded is false, meaning we are no longer on the ground. While to return to the ground, we create the transition from jump to the idle state, and we do it for run as well. And we set grounded to true. The exact same thing, set all values to 0 because we want immediate responsiveness. Let's go into the script. In the animate function, we write anim, set float, vSpeed, RB, volatility, y. Make sure it's the y-axis. And we also set that boolean. We are taking real data from physics and our laser sensors and feeding it to the animator. The code commands, the animation follows. Let's save everything, hit play, and look at the magic.